Here we are in Chapter 11, Section 4, Problem number 5. Here it is. The Mozart effect refers to a boost of average performance on tests for elementary school students, actually for any students, not just elementary school students, if the students listen to Mozart's chamber music for a period of time immediately before the test. In order to attempt to test whether the Mozart effect actually exists, an elementary school teacher conducted an experiment by dividing her third grade class of 15 students into 3 groups of 5. The first group was given an end-of-grade test without music. The second group listened to Mozart's chamber music for 10 minutes, and the third group listened to Mozart's chamber music for 20 minutes before the test. The scores of the 15 students are given below. Okay, there's the table of the 3 different groups. Using an ANOVA F-test at alpha equals 0.10, is there sufficient evidence in the data to suggest that the Mozart effect exists? So our level of significance of 0.1. Let's look at to see what we're going to do here. So we're doing an ANOVA F test, and we're testing, which means we're doing the hypothesis testing. So we have the normal set of 5 steps. Our first step is determining the null hypothesis and the alternative hypothesis. And in this case, when we're doing ANOVA tests, we're looking to test in the null is that all the means are going to be, so the sample means are going to be the same. And then alternative is that not all 3 sample means are the same. So there we got it. Our step 1, means are the same, or as an alternative they're not, and we're testing that at the 0.1 level of significance. So 2, identify our test statistic. In this case, we're doing an F-test, which is spelled out there. So if we actually look into this section 4, it tells us how to define the F-test. In this case, it's the MST over the MSE. So we're looking at the mean square for treatment divided by the mean square for error. And that's going to have particular degrees of freedom given on parameters of the problem we have here. Okay, so let's see how we're actually going to compute this. So if we look back either in OneNote or actually back into the text, we've got that section that actually spells out what the combined sample mean is and the combined sample total quantity, the mean square for treatment, the mean square for error. So we're going to need to be calculating all those different elements, then the n for each individual group, the average for each individual group, the variance for each individual group. And to me that says jump to a spreadsheet. And let's do all those calculations there, then come back over here and see what we've got in terms of how these things compare. So let's figure out what all those different variables are. We'll jump to Excel like we've done before. And here we are in Excel, and there's the whole answer. Okay, let's look at how I did that. So what I did was just jumped into Excel and typed the alpha in, just so I've got it with the other numbers that are important numbers for doing the F-test. Then I recreated that table that we just saw in the problem, the 5 values for the 5 students for each of the 3 groups. So put all those in. Then the first thing I did was came up with what are the number in each group. And it's obvious, right? You look at it and say in group 1, there are 1, 2, 3, 4, 5 samples. So there's n sub I, and I just put it ni in here in Excel to make it easier on me instead of trying to figure out how to do a subscript I. And I also did it, I just came in here, another way I could have done it is I did a count variable. So the I count goes through and counts the number of, adds up the value, or counts the number of cells that have something in them. So here's looking through that section, all those blue cells, how many of those cells have something in it. And it counts and counts 5. And I did that for each of those. Then I summed up to say how many total do we have. So what's our total, or I combined sample size. And what I did there was I just did a sum across the subgroups. And once again, you could have done that in your head just about right, because you had each group had 5 times 3, 15. Okay. Then I essentially did that here for my K, and the K being the number of different populations. So I have 3 different groups, 3 different populations or samples that I'm doing. And each of those different samples is from a different population. One had no music played, one had 10 minutes of music played, one had 20 minutes of music played. So they're three different populations, three different sets, so their K is 3. So by the definition that we have here in the text, our degrees of freedom 1 is K minus 1. So here I've got this pointing to K, and I'm subtracting 1 off that. Once again, so 3 minus 1 is 2. And then our degrees of freedom 2 is our total number of N, so the total combined sample size, and subtracting from that the number of different groups. So here I've got the blue cell B15 minus the red cell B16, so N minus K, which is what we just said. And that gives me 15 minus 3, or 12. Okay, there's some of the things calculated. Now I mentioned I'm going to have to calculate the means for each of the groups. So I've got here I've called it xi bar, so x sub I, so x1, x2, x3. So bar for x bar being the mean, so looking at what is the mean of group 1, the mean of group 2, the mean of group 3. To do that, I went ahead and used the function right out of Excel for calculating the mean, or the average of that sample. So here it's doing the average of the sample set from B8 to B12, so those values. And then I copied that over and got that same for doing it for group 2, and then the same thing doing the average for group 3. So my three different averages, they look a little different. I've got a 71.6, a 76, and an 80. Those seem a little different. Now I've got to do the whole X bar. And several different ways to do this in Excel. The first way I did it was I just did an average of that whole set of numbers. So they didn't have to be all in a row or a column. I did the matrix of the average of all those, and that gave me 76.1. I also did it, one of the ways they had, or another way here was looking at summing each of the columns. So here I've got the sum of the first column, plus the sum of the second column in red, plus the sum of the third column in purple, adding all those together across here in this formula, and dividing that by the total number of samples. So our total of the combined sample size of 15. And when I did that calculation, it came out the same value, 76.1. So that I didn't have to do it two ways here. That just confirmed it. Okay, now let's continue. So I'm going to be needing the variance, or the sigma squared, for each of the individual groups. So here I have the variance of the sample. Var S is for variance from a sample, the Excel function there. So what I did was I calculated the variance of group 1 using the Excel function for that. And likewise, I did that again for the group 2. So there it is, that var.s for group 2. And likewise for group 3. And there are my three different variances. Now I can start getting closer to this mean square for treatment, the MST, and the mean square for error. So when I look at the formula for the mean square of treatment, I've got this n1 times x1 bar minus x bar squared. So what I decided to do was just do that numerator thing for each of the different i's, so for group 1, group 2, and group 3. Then sum them all up and divide by the k minus 1 in the next step. So this is just that numerator, the one step in that piece. So what I had was the n1, so here's my n1, ni, so the number in group 1, that's B14 in blue. And then I multiply that by, here I'm going to have, let's see, the mean, so the mean x1, that's in red at B20, there's x1 bar, so that's the mean of group 1. I'm going to subtract from that the overall x bar. In this case, I put the dollar sign in front of the B because it's always going to be in column B. So even if I copy the formula over, it's still going to take stuff from there. So I'm taking the mean of the first group, subtracting from that the overall mean. Then I'm going to square that, so that's caret 2 to be that value squared, and then multiply that by the n. So that gives me the first term for, in the MST for 1. I do the same thing, so for 2. So for 2, I'm taking, again, the number in group 2 times the quantity here of, so C20, that's my x bar, minus, there it goes back over to column B again, that overall x bar. So the mean of the group 2 minus the overall mean, I'm going to square that and multiply that by the number. And do that again for group 3. We can go ahead and look at that. Ni times x bar, xi bar, so x3, the group 3 mean, minus the overall group mean. Squaring that gives me that value. Then what I'm going to do for my overall MST, my mean square for treatment, is I'm going to sum all those numerator pieces. So the nx1 x bar squared plus into all those pieces, which is that first row there, or the row just above where I am in blue. So summing each of those. And then I'm dividing that by k minus 1. You can see here in red that goes to get k, which is back up there in B16. And so that gets me the k, and I'm going to subtract off the 1 from that. So my MST is 89.87. Similar kind of thing I did for the MSE as well, the mean square for error. So in this case, I'm going to have for each one of the terms, I'm going to do that, calculate those, and then sum those, and then divide by the n minus k. All right, so for those, each individual element there, I've got, so here n1 minus 1. So n1 is in B14. There's n, and I'm going to subtract 1 from it. Then I multiply that by the variance, so the standard deviation squared, or the variance, which is what we calculated in above here in that var I. So the variance for group 1, the variance for group 2 next to it, and the variance for group 3 next to that. So in this case, it was just the blue minus 1 times the red got me the value of the 153.2 down here. Okay, same thing. So then for 2, I took the number of the sample size for group 2 and subtracted 1. So the blue, C14, minus 1 times the red, C23, which is the variance. And again, I did the same thing for group 3. Then to calculate the overall mean square for error, I sum across each of the terms. So the sample size times variance terms, which was that row just above in blue there. So I'm summing that row, and I'm dividing that by the quantity of n in red minus k in purple. So from B15 minus B16, dividing that into that sum that I just mentioned, and that gives me the value of 22.67. All right, I've got my MST and my MSE, and if we had looked back, we saw that F is the MST divided by MSE. So here it's blue divided by red, blue divided by red, MST divided by MSE. So my F statistic calculated out, which was step 3 in the process here, is 3.96. All right, let's jump back over to where I was writing here. And so as I calculate that out, my F equals 3.96. That's my calculated value of the F statistic that I'm using to test against the value that I'm going to find in my, to find my critical value range to see how that fits. So in step 4 here, I will go, so now I'm going to find f of alpha at the 2 different degrees of freedom values that I need to deal with here. So this is going to be f, and alpha was that 0.10. And we had calculated back here in the Excel sheet, let me jump back there again. See, degrees of freedom 1 was k minus 1, that was 2, and degrees of freedom 2 was n minus k, so 15 minus 3, that was 12, so 2 and 12. Let me jump back over here. So my degrees of freedom are at 2 and 12. So then I need to go look into the chapter 12, or that appendix where we have the different tables of values, and I'm going to look in the F statistic table, looking for F at 0.10, with degrees of freedom 1 being 2, which is across the top, and 12 being one of the rows, so column and row, in the for the 0.10, and I have to look in that table, and I find 2.81. So we mentioned this as a right tail test, so it's 2.81 to infinity, It's my rejection region. And so I can see that, yes, I do fall in the rejection region. So I reject the null hypothesis that all means are the same at the 0.10 level of significance, so that we know that sample means are not the same. So statistically speaking, we did not prove anything about the sample means in terms of which one's greater or which one is the least. What we determined was they are not the same. So there is a difference in these sample means that could be attributed to this Mozart effect. So that's where we are, number 5. Look forward to seeing how you do your example when you do that on homework.